So the first activity in this section is related to sort of thinking initially about the idea of what a directional derivative is and what it should represent, and how can we use a contour plot like the one we're seeing on the screen over here to the right. How can we use a contour plot to give us some initial kind of intuitions as to what directional derivatives should mean, and can we tell based on a contour plot when a particular directional derivative should be positive or should be negative, or possibly should be zero. So how we'll get started is by thinking about this function. F of x and y is 30 minus x squared minus half y squared. The authors of our book have helpfully given us a contour plot of that function, as well as marked a single point, 2, 1, at which we're going to be most interested in quantifying some directional derivatives. So parts A and B ask you, first of all, to quantify, and again, you can use the formula here rather than having to use the graph, and I think that's the intention. Quantify the instantaneous rate of change of temperature. So if this function represents temperature, what's the instantaneous rate of change of the temperature with respect to x, so as we're walking to the east. And part B is what's the instantaneous rate of change if we're walking to the north. And then part C is going to give us a direction in between. Instead of due east or due north, we're going to walk in a direction which is parallel to the vector 3, 4. Right, so that's going to be a northeasterly direction. That's a little bit more east than it is. Sorry, a little bit more north than it is east. And so in part C, you're going to begin to develop the tools for how to understand how a function of two variables, in this case, should be changing if we change its inputs simultaneously in the direction of a vector that doesn't point due east or due north. So why don't I give you the space to start on parts A and B, answer those instantaneous rates of change first. And then if you feel pretty good about that and we don't need to check in on that, you can go directly to part C and start doing the work that's there, which you might need to read through this paragraph once or twice to figure out how to get started on it, but it does a good job of sort of describing how to get going. All right, so in this problem, you first quantified the instantaneous rate of change of this function, this temperature function, if you like, if we walk to the east and if we walk to the north, and each of those instantaneous rates of change is one of the partial derivatives. Right? So in the x direction, the partial derivative function negative 2x at the point in question is negative 4. So if we walk to the east in this diagram, we end up decreasing in temperature by negative 4 degrees Celsius per foot. So we go down 4 degrees per foot as the temperature change if we walk to the east. If we walk to the north, the y partial derivative tells us that our temperature is going to decrease at a rate of 1 degree per foot. By the way, is there anything about this contour plot that could have told us that the y partial derivative is smaller in magnitude than the x partial derivative? So assuming that these contours are equally spaced apart z-values, which usually contour plots are, but that's something to always be careful about, that if these contours are equally spaced apart, then starting from 2, 1, the closest contour to the east is pretty close to us compared to the north. Right? If I want to reach the next contour, if I want to go either up or down, we can't tell from the contour plot, but we know now because of the partial derivatives that the contours are actually decreasing in z-value as I go away from the origin here. Then the next lowest contour is really close to me in the x direction, and so I'm dropping really quickly. Compared to in the y direction, the next closest contour down is pretty far away, and so I'm decreasing more slowly in the y direction. Okay. And so then to figure out what would happen if we were walking through this point along a velocity vector of 3, 4. So you parameterized a line with a velocity vector of 3, 4 going through this point, and then use the chain rule to find the derivative of the temperature function in that context. And the chain rule is nice to use because we already computed the partial derivatives of f with respect to x and y. And so the only difference then between those partial derivatives and the derivative of the temperature in that diagonal direction is just we're multiplying them by the velocity components. So multiply the x partial derivative by 3, multiply the y partial derivative by 4, and we end up getting negative 16. So negative 16 degrees Celsius per second. So let me ask the quick question here. What is the big difference in units between the partial derivatives that you computed in the beginning here and the time derivative that you computed in the last part? We have an understanding of how quickly the temperature is changing per second. So units here are degrees Celsius per second. But the partial derivatives are just slopes, right? And so they were the rates of change per foot. So distance is the denominator unit here, and time is the denominator unit on this one. So how can we travel in between those worlds? How can I use the rate of change per second? What information would I need in order to turn that into a rate of change per foot?
Oh, are you trying to get at is
So what I'm trying to get at is that your answer to this question here depended on the velocity. It depends on how fast that we were moving through this point, right? Where a slope doesn't care how fast we're moving. A slope is just a comparison of two lengths, right? It has nothing to do with time. So what I want us to try to think about is how might we wash the time component out of this and give us back a slope instead of a time rate of change, give us a distance rate of change again, like a slope is. And so when I say use the units, what I kind of have in mind here is that our answers to part A and B, the partial derivatives, were degrees Celsius per foot, right? And that's what we ultimately want to get to. But our answer to part D was degrees Celsius per second. So what relationship, what could I do to degrees Celsius per second to turn it into degrees Celsius per foot? I don't know if you've done this kind of dimensional analysis before, but whenever we have units, the units can always sort of help give us a suggestion as to what arithmetic that we could do to get a quantity with the units that we want, starting from a quantity with the units that we have, which is degrees Celsius per second. So I need to replace these seconds by feet. What kind of unit
We
would I
could
want?
do some sort of second over foot.
Yeah, so I would want to somehow get a quantity which is in seconds per foot and multiply by that, right? But seconds per foot seems kind of like an odd comparison. But what about if instead of multiplying by seconds per foot, what if instead we could divide? Well, multiplying is the same as dividing by the reciprocal, right? And if I reciprocate the second unit, it becomes feet per second. And that feels like something that is more recognizable. So what quantity might we have in our parametric curve here that could tell us feet per second as we passed through the point in question? Another way to see this might be to go back into this chain rule calculation one more time and really mine this equation for gold here. So the df dt over here on the left side of the equation, that's a rate of change that's being measured in degrees Celsius per second, right? But meanwhile, the partial derivative df dx, that has units of degrees Celsius per foot, right? But then we end up multiplying it by dx dt. And so if x has units of feet and t has units of second, then what does dx dt have for units? The numerator is feet, the denominator is seconds. So I guess what I'm trying to get at here is that if we're looking for something that has units of feet per second, we should be looking at the velocities of our parametric curve. Right? The problem is that dx dt only tells us the velocity in the east-west direction. dy dt would only tell us the velocity in the north-south direction. And if I really want to understand what is the the slope of this line, then what I want here is I want to know how fast was I actually moving in total, not just in the x direction, not just in the y direction, but how fast am I moving as I pass through this point. How do I find that for a parametric curve again? How do I compute the speed at which I'm moving? So what we would like to do in order to wash that speed aspect out of our parameterization and recover a slope is we need to divide by the speed. And we can find the speed by finding the magnitude of the velocity vector. So our velocity vector was 3, 4 in this problem. And the magnitude of that vector is right here. Magnitude of v is square root of 3 squared plus 4 squared, which is the square root of 25, which is 5. So that's, I think, the reason that the authors put this note in the statement to part C. Note that this person's speed is 5 feet per second. So if we know that that person is experiencing a temperature change of negative 16 degrees per second, then to figure out how the temperature is changing per foot, all we have to do is take that negative 16 degrees Celsius per second and then divide it by that person's speed, which is 5 feet per second. And when we do that division, negative 3.2 degrees per foot would be then how we would recover the space rate of change of the temperature per unit distance, not per unit time. And that is ultimately, so this is division, so I'm going to put here divide by the speed, i.e. the length of the velocity vector. Magnitude, let's use the appropriate term here. Dividing by that magnitude makes sure that the magnitude of the velocity vector that we choose doesn't matter anymore. The only thing that matters is the space, basically the slope, right? The relationship of the change in the z variable, the f output, to changes in the x and y input. And so that is ultimately the slope. That's ultimately the kind of quantity that we want to equip ourselves to study, right? Because ultimately, in this picture, right, there's no, here I am at the point 2, 1. Let's put in that velocity vector of 4, 3. Stretch that, 3, 4 rather. Stretch this out here. There's my 3, 4 velocity vector. And so that velocity vector is really long, right? Which is part of the reason why that directional derivative ends up being so large and negative. But ultimately, the directional derivative is not that time rate of change, it's just this slope. And that slope, as it says here on this diagram here, really is just negative 3.2. So we want our answer not to depend on how long our direction vector is. It should only depend on the direction vector itself. And so if we choose a longer or shorter direction vector, as long as it's parallel, it's not going to change the value of that slope of the tangent line to our graph. So that's why ultimately we end up dividing by that magnitude, so that the magnitude doesn't matter anymore. This is a lot of what mathematicians do when they create a new way of trying to compute something, is if you have to make choices along the way in your computation, very often you want to make sure that your answer doesn't depend upon the choices that you made. Like, if I'm looking for the slope of a tangent line, I want it not to matter how large or small is the direction vector that I choose to represent that line, right? The direction should be the only thing that matters, not the magnitude. And so we should check, as we sort of did here, right, that the way that we define this quantity is in such a way that only the direction that we're walking in matters, and not the magnitude of the vector that we use to represent the direction that we're walking.